Okay, we talk about inverse functions. We start with a simple example. Y equals f of x equals 3x minus 7. Now I wrote that down because it's easy to invert, and it's typical of the questions you answered on your homework. And people did quite well with this, so I think there's very little problem with this. That actually turned out to be a bad choice because when I tried to graph it, I had to use a whole lot of board. But we'll go along with that. Okay, so if we have this function, but then we have, of course, y equals 3x minus 7. We invert it by switching the x and the y, and we solve just by adding 7 to both sides and dividing both sides by 3. We get x plus 7 over 3, quantity x plus 7 over 3. So the inverse function is x plus 7 over 3. We verify that. F of f inverse of x should end up equaling x, and in this case it does. F of x is 3x minus 7, so f of f inverse of x is f of x plus 3 over 7. Since f of x is 3x minus 7, f of x plus 7 over 3 is 3 times x plus 7 over 3 minus 7. And that simplifies and simplifies again and gives us x. Now to officially confirm that we have the inverse function, we would want to do f inverse of f of x, but that works out very similarly. And from the skills that people are exhibiting in this course, I don't see that it's going to be any problem to do that. Okay, now I went ahead and constructed the inverse function, or the function and its inverse, and that's where I saw that I wish I'd have chosen smaller numbers there, but we're going to do it anyway. Okay, so here's our y equals x line. Okay, now that's a toolkit function, y equals x. We construct this by saying that this is a vertical stretch of the y equals x function by factor 3, and then a vertical shift of negative 7. So we construct the inverse by vertically stretching this function by a factor of 3. We see that the point 1, 1 goes up to 1, 3. The point negative 1 goes to 1, negative 1, negative 3. Now that's with numbers, but if we just do it geometrically, we can see, for example, that if x is this value, which looks about 1/2, maybe 0.4, the y value is represented by this tiny arrow here. And if we pile another tiny arrow and another on top of it, then we get the y value if this function is vertically stretched by factor 3. And that's something we've done in class. So we get the idea. And we could do that for a whole series of points on the f of x graph. A whole series of x values between negative 2 and 2. We do the arrow, and then we can triple the arrow like we could do here, and so forth. So presumably that's something you understand how to do and have known how to do. Having done that, we then shift every point of this green graph 7 units downward. You see some arrows here. And we have our constructed graph. Now the constructed graph didn't come out as accurately as we wish because when we try to demonstrate how the points here reflect across this line to give us these points, it doesn't quite work out. For example, if we try to reflect this point on the line that I constructed across here, it ends up about here. It actually ends up here somewhere, not quite on the graph of the x plus 7 over 3 function. Now, let's back up. I constructed this function by vertically stretching, or vertical compression, but you have this 1/3 factor. I like to call it a vertical stretch by factor 1/3, which does end up a vertical compression. Your book uses slightly different terminology, but we take the y equals x graph and we construct the y equals x over 3 graph, multiplying by 1/3, compressing the graph by a factor of 3. Gives us this graph, and then we raise it 7/3, we get this graph. So this should be the inverse to this, meaning that every point here should reflect at a perpendicular across the y equals x line, equal distance on the other side to a point on this graph. Doesn't work out too well for this point. If we go to perpendicular, we're going about there, and then we go here, we get a point here. It's close to the graph of the inverse function, but it's not really inverse to this point. If you switch the coordinates to this point, you don't get this one. A more accurate point on this graph, when we get to here, would be over a little closer here. And if this is reflected, it ends up here, and it's just a little better. If we continue to graph on, you see that the two graphs are going to meet at a point that's pretty close to the y equals x line, but this graph should have a slightly steeper slope so that the two graphs really ought to meet about here. Okay, so you can kind of reconcile that. Picture didn't come out as nicely as I'd like it to, but it's not that far off. Okay, so anyhow, this is a geometric construction of a function and its inverse. If we do tables, well, that's very simple. I just did a simple table, -2, -1, 0, 1, 2. For the f of x function, getting these values, which are very easy, just plug into the function. And then we reverse the values, and we see that every one of these points fits here. If we plug in 13 for x, we get -2. Plug in -10 for x, simplify, we get -1. You should verify that. So that's kind of it. Now, we then moved on to inverting the function, the basic cubic function, okay, y equals x cubed. To invert that, well, we switch the x and y coordinates, we get x equals y cubed. And how do we solve this? Okay, and then it became clear that people had a little bit of trouble with this, so we really need to understand this. That's something you need to focus on. We take the 1/3 power of both sides. Okay, now you could say you take the cube root of both sides. I don't use radicals a whole lot. Simply because you can't type in a radical. Okay, and then of course like this, sometimes you got to type things in. If you want to write them out with radicals, that's fine. But radicals are just an expression of fractional powers, and you have laws of exponents that apply to fractional powers. And I prefer to stay with the laws of exponents rather than getting a whole new set of laws for radicals. Just see a radical as a fractional exponent. And apply the laws of exponents. You don't have to learn anything new to do that. So, we take the 1/3 power of both sides. Okay, now we rewrite the equation y cubed equals x. We're solving for y. We like to see y on the left side, although it's not necessary. Excuse me. We take the 1/3 power of both sides. We get y cubed to the 1/3. Now, why did we take the 1/3 power? Well, because y cubed to the 1/3 is just y to the 1, which is y. To see that, y cubed to the 1/3, by your rules of exponents, a power of a power, you multiply the powers. Y cubed to the 1/3 is y to the 3 times 1/3. So, there it is. 3 times 1/3 is 1, and y to the 1 is y. And all the way down you have x to the 1/3 here. Then if you want to write that as the cube root of x using radical notation, I don't have any objection to it. Can't type it, but in the laws of exponents, you almost have to change over to exponential notation to fractional exponents in order to apply the laws of exponents. However, the laws of radicals are parallel to the laws of exponents. It's easy to translate from one to the other. So if you like radicals, please use them. Sometimes it's actually necessary. Okay, we went on to beat this x cubed function to death by writing its table and writing the table of the inverse by inverting, and also by confirming that f inverse of x, f of f inverse of x composed with f inverse of x, gives you x. And that's very simple. F of x is x cubed. F inverse of x we say is x to the 1/3, and the table corresponds to that. The 1/3 power or cube root of -8 is -2, of -1 is -1, and so forth. Okay, so doing f of f inverse of x, f inverse of x is x to the 1/3 or cube root of x. So f of f inverse of x is f of x to the 1/3. F of x is x cubed. So f of x to the 1/3 is x to the 1/3 cubed, giving you x to the 1/3 times 3 is x to the 1, which is x, confirming that we have an inverse function. To totally confirm it, you'd have to do f inverse of x, and all that would happen is you'd have the cube here and the 1/3 power here, and it would come out the same. I then constructed the graph of x to the 1/3 by drawing the y equals x line, and this one worked out a lot better. It's not totally accurate, but we sketched a graph of x to the 1/3 using the table, and then we simply reflected points across the y equals x line. Now it's kind of faint, I'm sure you can probably see it, but right here we took this point, and reflected across this line to get this point. Take this point and reflect across this line, and we get this point. If the graph is drawn equally with equal scales, which is more or less but not quite true, and these projections are made perpendicular to the y equals x line, this distance is the same as this distance. This is perpendicular. This distance is the same as this distance. Same here, perpendicular. This distance should be the same as this distance. We could do that with every point. We can do that with points up here. We could take a point here and reflect it and get a point here. And the graph that we get fits the table of the y equals x to the 1/3 graph pretty well. Okay. Well, we went on to talk about what happens if you try to do an inverse function for y equals x cubed, x squared. Now what we did was we constructed the inverse function first for this point and this point and this point. The points 2, 4. The point 2, 4 became the point 4, 2. Point 1, 1 became the point 1, 1. The point 1/2, 1/4 became 1/4, 1/2. And we observed that those projections had the necessary characteristic being perpendicular to the y equals x line and equal distance on both sides. So we constructed this much of the graph and said, so far we've got us a good function. Then we did the same thing with the points on this side, and we got 3 more points down here. And then I said, well, whoa. This is not a function. It doesn't obey the vertical line test. Okay? We call it an inverse relation. In order to get an inverse function, well, we could get an inverse function by simply restricting the domain to this much of the curve, which gave us this curve here, which by itself without this part made a perfectly good function. Okay? Well, if the domain of f of x then is restricted to the interval 0, 2, here's the interval 0, 2, you get the points in purple. If you invert that part of the graph, you get this red graph, which is a function, and we call that, first of all, this branch of the inverse relation is a function. So you got the inverse relation, two branches, a branch that goes this way, a branch that goes this way. In the original function, you got a branch here and a branch here. If you restrict yourself to this branch, you get this branch of the inverse relation, which is a function. You restrict yourself to this branch by restricting the domain to the interval 0, 2. And now the inverse becomes a function. And that function has a name, which I didn't mention in class. It's a big deal. The inverse function this inverse function is the square root function. Okay? Well, if we then use that function to solve x squared equals 4 for x, well, just take the equation x squared equals 4, and we want to solve that for x. And I'm going to address that in another video, because I've got to stop right now and send out an invitation, because I'm a little over time in sending it out an invitation for class that starts in 6 minutes. So, hang on a minute.